Hey guys, my name is Osama Samara, and today we're gonna use Castigliano's second theorem to find the deflection of a curved beam. So in this problem, we're given basically a wire ABC, and we're asked to find the vertical deflection at point A due to this force P right here. And first thing we have to notice is that this is actually a wire, so we can neglect the normal or the deflection from the normal and tangential forces at our section cut, and we can neglect the eccentricity basically. So when the problem states it's a wire, means that the radius r over the thickness is larger than 10. So when this holds, you have a wire, and you only consider the bending moment when you're trying to find the deflection. Right, so by looking at this problem, we need to find the deflection at point A. So let's start moving from point A all the way to point B. We have a load change, right? And in order to use Castigliano's theorem, we need to apply a dummy load at point A, right? Let's call it Q. Let me use a different color. Let's call this force Q. And the reason why we applied the dummy load at point A is that in order to use Castigliano's theorem, you need a dummy load at the point of interest where you're trying to calculate the deflection. So at point A, we didn't have a concentrated load. That's why we applied dummy load Q. So we need a section cut. Let's call this section cut AB. And since the load changed with force P, we need another section cut here. And let's call this one BC, basically. So let's analyze each section cut by itself. So let's move down here. And this is section AB. And let me try to draw the free body diagram of section AB. Right, it looks something like this, and you have a dummy load Q right at point A. So this is point A, and you have a moment. Let's call this one moment 1. And you have O right here, and the radius is R. Right, so we're trying to find the moment. So Mi is gonna be equal force times distance, right? And we're looking for this distance. So if you consider the line of action of this force is going in the vertical direction, right? And you have this radius right here, R. And you've extend this from the centroid right here. And so we're looking for this distance. So let me use a different color. We're looking for this distance from the centroid to the line of action of the force, right? Because that's the definition of moment. Right, so we're looking for this distance, and it's basically, if you use some trigonometry, right, if you extend this R right here, so this is also R from the centroid O to the centroid of the wire. This is R, or the distance as the problem stated, the distance from center O to the centroid of the wire is R. So we need this distance. So this yellow line right here is equal to this one, right? And you can call this angle right here to be theta. As you recall, for moment mi, the way I drew it, it's in counterclockwise, so I'm assuming it's positive. And it's gonna be plus, right? Q times the yellow distance that I drew, and the yellow distance is equal to R, the entire radius from O to point A, so R minus this black distance, or this black line right here, and this one is R cosine theta. This is gonna be equal to 0, right, in equilibrium. So let's solve for mi. Mi is gonna be equal to negative Q R minus R cosine theta. Okay, and we need to take the partial derivative, right? dmi or dm1 over dq is going to be equal to minus r1 cosine theta. So we need this one in order to apply Castigliano's theorem, and this one, the moment and the partial derivative of the moment with respect to the force or the applied dummy load Q. Right, and this is for the first segment or section cut AB. Let's try to draw section cut BC. So for section cut BC, it's gonna look something like this, and here is theta prime. And the reason I call this one theta prime is because we already used theta in section cut AB, and we called this one right here to be theta. Right, so we call this one theta prime just for convenience when we're trying to solve the problem. And you have a moment, right, m2, and remember we're neglecting the tangential force and the normal force along with the effect of eccentricity. So we only consider the moment because we're dealing with a wire. So m2 is going to be positive the way I drew it. It's counterclockwise. So m2 plus q times this entire distance, r plus r sine theta. Right? And plus P times the yellow distance, or the yellow line, R sine theta, is going to be equal to 0 because of equilibrium. So M2 is going to be equal to negative QR plus R sine theta minus PR sine theta. And the partial derivative of M2 with respect to dummy load Q is going to be equal to negative R1 plus sine theta, right? Because the partial derivative of this term with respect to Q is going to be 0, right? Okay, so we need this one, right, to use Castigliano's theorem, and this one. So let me try to fix that. Oh. We need this one and that one. Okay, now we can apply Castigliano's theorem. Right, so let's write down the formula. So the deflection at point A, delta A, is going to be equal to 1 over EI, the integral from 0 to pi over 2. And why did we pick pi over 2? Because remember, this theta right here is going all the way from 0, horizontal, right, all the way to 90 degrees. So this theta is going from 0 to 90 degrees, pi over 2, times m1 dm1 over dq r d theta plus the second section cut 1 over EI, the integral from 0 to pi over 2 m2 dm2 over dq or d theta prime. And this one should be theta prime, right? So yeah, this one right here should be theta prime, just to distinguish it from the theta we used in section AB. Right, so you just plug in all the terms for M1 and M2, and for dm1 dq and dm2 dq. So 1 over EI, the integral from 0 to pi over 2 q r squared 1 minus cosine theta squared r d theta. This is the first section cut, AB, plus 1 over EI, the integral from 0 to pi over 2 QR 1 plus sine theta prime, right? Theta prime plus PR sine theta prime, and this is times R 1 plus sine theta prime R d theta prime, right? So let me try to fix this from 0 to pi over 2, right? And remember, for Q, it's a dummy load, so it's 0. So basically this one is 0. So this whole term, section AB, is 0, right? And it makes sense. If you go back to the problem, a section AB without the dummy load, right, it's a free end. That's why it's 0 according to Castigliano's theorem. The deflection there is 0 in section AB because it's a free end. The deflection is coming from load P, so section BC. Right, so also here, whenever you see Q, you're gonna just plug in 0 for Q because it's a dummy load. There is no value for Q. Okay, and if you do the integration, if you simplify and do the integration, you'll end up with this. So let me simplify it. 1 over EI, the integral from 0 to pi over 2 Q R squared 1 minus cosine, or no, it's gonna be P, right? Q is 0. Q is a dummy load, so it's gonna be P here, P R cubed sine theta times 1 plus sine theta d theta, and this should be prime, right? So this turns out to be what? If you do the integration, it comes out to be P R cubed over EI times pi over 4 plus 1. Right, and here's your deflection at point A due to the load P. Okay, hope you found this video to be helpful. Thank you. Take care.